Hi, I'm Rob, and this is our 15th lesson in the topic of trigonometry. And in this lesson, what we're going to take a look at is applications of trigonometric graphs. And in the previous lesson, we had a look at what trigonometric graphs look like. We had a look at the four basic shapes, sine and cosine, negative sine and negative cosine. And in this lesson, we're going to have a look at some practical applications of that. And these applications begin in your notes on page 204. So if you look at the first question there on page 204, it looks like this. It says, giant wheel is a Ferris wheel, one of the largest in North America, found in the Cedar Park amusement park in Sandusky, Ohio. The height above the ground, h in meters, of one of the 36 passenger gondolas can be modeled by the following function. So here's our function here, h of t is equal to 22 minus 19 times cosine pi over 32t, where t is a real number and t is greater than or equal to 0. And we're told t is the time in seconds, and that pi over 32t is expressed in radians. So I'm being told that it's expressed in radians. So we're asked to first of all complete the table there. So in order to complete the table there, what I'm going to do first is I'm going to use my the table function of my calculator. All right. So if I bring up my calculator here to use the table function, what I'm going to do, remember, is I want to press the home button here in the top left-hand corner, and over on the right-hand side there is a table, so I'll go sideways twice with the right side directional arrow to bring me over to the table, then press OK. And here's the table here, so you can see that the two things that are missing, that I don't yet have a set of x values going down here, and I don't yet have the function typed in either. I have to do both of those now, and it doesn't matter what order we need to do them in. Notice as well that at the moment my calculator is still in degree mode with the D up here. So I'm going to have to change that. Okay, well, that's the reason why the examiner mentions in radian, just as a reminder of that, just to switch your calculator into radian mode there. So to put the calculator into radian mode, I want to press the settings button in the top left-hand corner, and the angle unit the unit of measurement for angles is a calculator setting. So I just want to press OK there, and you can see the second option down here is angle unit. So if I go down one to angle unit and press OK, you can see at the moment degrees are highlighted. The calculator's in degree mode. So I press the downward arrow and then press OK. So it's in radian mode, and now I just press AC there. You can see now we're back, and now the calculator, as you can see, is in radian mode, because there's an or at the top. So make sure you switch your calculator to radian mode once you see in the question that that everything's measured in radians. So in order to type in the function, what I want to do first is I want to press the tools button. And the two things you'll notice here, the top one here is the table range. That's the list of numbers I'm going to type in. I'm going to get the calculator to drop into the formula. And then to define the f of x and g of x, that's the second option. So I'll go down here to define f of x and g of x, press OK, and I just want to define f of x. So now f of x equals, I just type the formula in exactly as it appears on the page in front of me. So it's 22 minus 19 times cosine. So press the cosine button up here, opens the bracket. Okay, then I want to bring up a fraction. All right, so I want to put my pi above the line. So remember, pi is above the number 7 here. So I press shift and the number 7. There's the pi button. Okay, go down below the line there and then put the 32 downstairs that way. And then just go sideways here. And the X I'm looking for, you can see, is below the shift button, below the blue shift button. There's the X there. So the formula looks exactly as it does on the page in front of me once I close the bracket there. The only difference is that wherever there was the letter T in the original function, I've put the letter X in. So in a moment now, the calculator will drop in the numbers everywhere I put the letter X. So now I'll just press OK there. And you can see now f of x none is gone from the bottom of the screen because f of x has been defined. Right, so you type in the function first, you just press the tools button and define f of x. So now to define the set of numbers I want to throw in, press the tools button again, and table range at the top there. So we'll press OK, and this is where you want to start and finish. So if you look at your table here, you notice your table here, the numbers across the top of your table, they start at 0. Okay, so I'll press 0 and hit OK. And then you can see the last number of the table is 128. So I'll type that in. So we're going as far as 128, 128. And again, press OK. And the step is what we want to go up in. So you can see the step here is 16. We're going up in 16s. We go 0, 16, 32. The step is 16. So I'll put in 16 and then press OK. And the calculator says, now, do you want to execute? So I'll press OK like that. And there's my table. So you can see going down the left-hand column here, there's all the numbers that are across the top of my table. 0, 16, 32, 48. And then here in the right-hand column, there's the answers. 3, 22, 41, and so on. So they're the numbers I just transfer into the table on my page. So at 0, it was 3. 16, it's 22. Then it's 41. Okay. Then it's back to 22. It's back to 3. Back to 22. Up to 22 again. 41, 22, and 3. Right? And then if I plot those points on the graph, you can see 0, 3 is kind of down there somewhere. All right. 16, 22 is there. And 32, 41 is up there. Then 48, 16, or 48, 22, I should say, is there. 64, 3 is down here. 80, 22 is up there. 96, 41 is up here. 112, 22 is there. And then we're back down here at 3 again. And then just kind of very roughly, I mean, it'll be quite rough here. Just draw a graph like that, coming up here. And like that. So something like that. And you can see it's a negative cosine graph. I remember from the last lesson that the negative cosine graph is the one that's shaped like that. The one that starts, the bottom goes up and then down again. So the shape of the graph we have there fits perfectly. So that's what my graph looks like there. And that's kind of cheap and easy marks to draw a graph to begin with. Okay. So you can see then when we get to part 2 on the next page. So part 2 is how long does it take for the wheel to complete one full revolution? Well, you'll notice from your graph, you look at the graph a moment ago, you can see that the graph goes up like that and then back down like this. And it does that, you can see there after 64 seconds, because then it does the same again like that, okay, to bring you up to 128. That's 2 full revolutions. All right, so from the graph or from your table, the time it takes to complete one full revolution is 64, but make sure you include your units of measurement. It's 64 seconds. Okay, so it takes 64 seconds to complete one full revolution, right? Now, part 3 finds the maximum minimum heights of the gondola above the ground. Well, again, I can get those from the graph. You notice from your graph here that the lowest point there was 3. So when the gondola is at the bottom of the wheel, you're 3 meters off the deck. And then at the top here, you can see if I go across the top like that, it's 41. Okay, so the maximum there is 41. And again, practical question, include your units. It's 41 meters. And the minimum is 3 meters. So just get the top and bottom points from my graph. Okay, so it's quite easy to write those down. And then part 4, it says find the first 2 times when the gondola is 34 meters above the ground. So your formula number looks like this. It's h of t is equal to 22 minus 19 times cosine pi over 32 t. Okay, everything's in radians here. So I'm asked to find the first 2 times when the gondola is 34 meters above the ground. Now I guess I could, if I want to, I could go to my graph and locate 34 over here and go sideways. You can see, because there's 1 there, there's the first time when it's 34 meters, and then it hits 34 meters again here on the way back down again. And then obviously it'll be 34 meters again on the way back up, on the way back down. So we're looking for the first 2 times here when it's 34 meters off the ground. So I could do it from my graph, but my graph would just be an estimate, because how accurate my answers are there would depend on how accurately I've managed to draw my graph. So I'm better off using the formula here. So I'd only really use a graph in an exam if an examiner specifically asked me to. If he says using your graph, it means he's willing to accept the level of accuracy that your graph will give you. If he doesn't say that, he probably wants your answer a bit more accurately. So I'd be very disinclined to use the graph unless he specifically tells me to. Okay, so I'm going to use the formula here. So remember, this is the height here, and that's the time. So if I put the height here equal to 34 and solve. So I get 34 is equal to 22 minus 19 times cosine pi over 32t. And all I want to do now is find the value of t. Solve for that. So I'll start off by subtracting 22 from both sides, which brings the 22 over onto the left. So I get 34 minus 22 is 12. So I get 12 is equal to minus 19 times cosine pi over 32t, like that. Now, we'll divide across by this number here to get rid of it from the right-hand side. So I get 12 over minus 19 is equal to cosine pi over 32t, right? And now remember, at this stage, then that's a trigonometric equation now. Cosine something equals a number. And as we'll be looking at it in the next lesson, that solving trigonometric equations like that is something I need to be able to do to produce more than one solution. It's the one where you use the SATC circle or whatever way you learned that. I'll show you a slightly different way of doing that in the next lesson. So you're kind of saying, well, look, that's the same idea here. I'm looking for two solutions. In a real world problem, I wouldn't bother doing it that way. I'm just going to go ahead and find one value for t, and then what I'll always do is try and use the shape of my graph to puzzle out the other one. I think there's kind of less can go wrong if I do it that way in exam. Just get the t by itself. So to remove the cosine here, I'll go with the inverse cosine on both sides. So the inverse cosine of 12 over minus 19 will just equal pi over 32t. So to remove the cosine, I'll go with inverse cosine on both sides. And if I put this into my calculator, making sure my calculator is in radian mode, which it is anyway, because I set it into radian mode when I was doing the table a moment ago, that if I get the inverse cosine of 12 over minus 19, it comes out at about 2.254, like that. And then just divide your answer by pi over 32. So if I divide 2.254 by pi over 32, it comes out at about 22.9627. Let's call that 23. So that's about 23 seconds is the first time. Okay, so that's the first time here. So that's 23 seconds there, if you like. So after 23 seconds, the gondola is 34 meters off the ground on the way up. The question is, what's this time here? The second one on the way back down again. Well, the simple way to find out, remember, is to remember that your graph is symmetrical, right? So you can see this rotation of the wheel here is symmetrical, all right? So the right and left-hand sides are mirror images of one another. So if this first time here is 23 seconds in from the left-hand side, the other one would be 23 seconds in from the right-hand side. Because if I fold the graph over, the right and left-hand sides would fit perfectly on top of one another. So it's coming in 23 seconds from the left-hand side gives me the first time. Coming in 23 seconds on the right-hand side will give me the other one. And remember, if I'm coming in 23 seconds here, that's 64 minus 23. So that one's 41. So the second time then is 64 minus 23, which is 41 seconds. So there's the two times, the first two times, when the passenger gondola is 34 meters above the ground. That's a better way of doing that one. Just solve the equation to find t, and then use the shape of your graph to puzzle out what the other one is. There's kind of less can go wrong if I do it that way. Okay, and then just to finish that question up, then part 5, find the height of the gondola above the ground after 4 minutes. Well, again, if I use my formula here, then remember the formula looks like that. That it's h of t is equal to 22 minus 19 times cosine pi over 32t. Remember that then the number on this side here, their heights. So in the previous question, the number given the question was 34 meters. That's a height. So that was going on the left-hand side to solve. This number here, that's a time. So this time I'm given a time value, and I'm asked to throw that in to see how long it takes. So 4 meters here, or sorry, 4 minutes here. So I'm going to sub the value in there and say that the height at that time there is 22 minus 19 times cosine pi over 32. Now just be careful here, don't put it in as 4. Ask yourself, would you have made that mistake? That it says after 4 minutes. If you read the question carefully, remember it tells you in the formula, that in the formula, t represents the time in seconds. So watch out for the units there, make sure the units match. So if I want to convert, it's just 4 by 60, which is 240 seconds. So 4 minutes is 240 seconds. So I want to put in 240 like that. And now the right-hand side here is all numbers. I can just dump that straight into my calculator and it comes out at 22 meters. So 22 meters off the ground after 240 seconds, which is 4 minutes. And then finally, part 6, it says the function modeling the change in height of the gondola changed to this. So the formula changes to this. H of t is equal to 22 minus 19 times cosine pi over 36t. It said, how had the movement of the great wheel changed, and explain your answer. Now, if you remember in the previous lesson, what we talked about, if I was trying to draw, there's the original function there, and you can see the 22 is still the same, the minus 19 is still the same, the cosine is still the same here. It's this number here has changed. And if you remember from the previous lesson, what that number there tells you, the number in front of the t there, this number here, remember, tells you the central line of your graph, which is 22. And you can confirm that if you look at the graph you sketched in part 1, the center line is 22. This number here is your amplitude. It's how far above and below the center line your graph goes. So it's going to go up and down by 19. So if you go up by 19, it'll bring you up to 41. That makes sense. We saw that in the graph. And if you go down by 19, 22 minus 19 is 3. Brings you down to 3. That makes sense. So that's your center line, your amplitude. This one here tells you what the period is. So a full circle divided by this number here gives you the period. So in the original, you can see here that a full circle, which is 2 pi, because we're working in radians, divided by that number there, divided by pi over 32, gives me 64. And 64 seconds is the period. We saw that from our graph and from an earlier part of the question. So for the original movement of the passenger gondola on the wheel, a full revolution takes 64 seconds. If I change that number there, I'm going to change the period. So in this case here, you can see that it'll be 2 pi or divided by this number here, pi over 36. And that comes out at 72 seconds. So when we change that number there to pi over 36, the period changes to 72 seconds. So originally the wheel was taking 64 seconds to make a full revolution. Now it's taking 72 seconds. So it's now taking longer for the wheel to complete one full revolution. That means the wheel is turning more slowly, or has slowed down, or it's taking longer to complete a revolution. Make sure you mention something like that. You must make it clear how don't just kind of put these numbers down. You were asked how the movement of the wheel has changed. It's now turning more slowly. It's taking longer for the wheel to complete one full revolution. So that's a nice little question that brings a lot of this together. So the second question there, then on page 207, okay? It says the temperature measured at the South Pole varies sinusoidally with time over the course of a year. It can be approximately modeled by the following formula. And the formula we got this time looks like this. It's y equals 18.6 times sine pi over 26t minus 1.8. And again, we're told that it's for all time values bigger than or equal to 0. Okay, so we're just starting at this particular time point, where y is the temperature. So that's the temperature in degrees Celsius. And t is the time in weeks. That's the time in weeks there. And again, it tells you that pi over 26t is measured in radians. So if I hadn't already done so now, I'd go to my calculator and switch it to radian mode to make sure I'm clear on that, right? Now, if I'm dealing with a question of this type, once I see a formula like this, I didn't do it in the previous question because I was asked to draw the graph anyway, but I would always sketch the graph first. So even though I don't have to here, it just kind of helps you make sense of answers. And when you start doing things like calculus with this later in the course, it just makes a little bit more sense of your answer, that I can see when, for example, the temperature should be rising or should be decreasing. My graph will tell me that if I'm trying to find rates later on. But very often you're answering part of the question without even realizing it. So what does that graph look like? Well, first of all, look at the basic shape as we did in the previous lesson. It's a sine graph, right? And the number in front is a positive number, so it's a positive sine graph. Remember the basic shape of a positive sine graph, okay? It's the one that looks like this. It starts in the middle, it goes up in an N, and it goes down in a U. And then that basic shape repeats itself over and over again in both directions, right? In this case, it's only going this way because we're only dealing with positive t values. The negative part of the graph doesn't exist, but it'll keep going like this if we were to continue going in the right-hand side direction, okay? So remember, a negative sine graph would start in the middle and go down first, and then it would be that graph upside down. A cosine graph would start at the top, come down and go back up like that, and a negative cosine graph would start at the bottom, like the one we had in the previous question. Okay, but that's the basic shape of a sine graph. That's the basic shape drawn. Now, secondly, then remember the number by itself, the constant is your center line, like we did in the previous lesson. So there's the number by itself, minus 1.8. That's my center line. So minus 1.8 is my center line here. So the number by itself is the center line of your graph. And then this number here, the number in front of the word sine or cosine, that's your amplitude. That's how far above and below the center line of your graph the graph will go. So it's going to go up by 18.6, right, like that. And it's going to go down by 18.6. That's the amplitude there. So if I go up by 18.6, that brings me up as high as 16.8. Okay, so 1.8 plus 18.6, 16.8. And 1.8 minus 18.6 brings me down to minus 20.4. Okay, so we're going up and down like that. Now, notice in part 1 of the question, when we haven't even read the question yet, when I get to part 1, it says find the maximum and minimum temperatures measured at the South Pole over the course of the year. Done that. Sketch has done that for me. So I've already kind of puzzled that out. We'll get to that now in a second. Okay? But finally then the period. After how long does this pattern begin repeating itself? Well, like we met in the previous lesson and in the previous question, in fact, okay, remember that to find the period of a graph, you divide a full circle by this number here. Okay, so a full circle divided by that number there. So a full circle again is 2 pi because we're working in radians. And we'll divide by that number there, divided by pi over 26. If you pop that into your calculator, you get 52. Okay, so it's 52 and it's in weeks, and that makes sense. We're on a yearly cycle, and a year is pretty much 52 weeks. So that's what the graph looks like. So I wasn't actually asked to do that, but that always helps. It just makes sense of the information given in the question before I get stuck in. So now if I start looking at the question, so part 1 says, find the maximum and minimum temperatures measured at the South Pole over the course of the year. Again, when you see the word maximum, minimum, that can mean calculus. And in fact, I can do this using differential calculus. If you've already looked at calculus, you know you can do that. But I don't need to. I've got that from the graph here. So the maximum you can see there from my graph is 16.8. And remember, it's a practical question. It has units, so it's degrees Celsius. And the minimum temperature over the course of the year is this guy down here. It's minus 20.4. And again, that's in degrees Celsius. So over the course of the year, it's minus 20.4 is the minimum, and 16.8 is the maximum, right? Then part 2, it says, find the temperature at the South Pole on Christmas Day, December 25th, which is 299 days after the start of March. So this observation, time 0 is the start of March. Right? We're asking what's the temperature after 299 days. Now again, like the previous question, be careful of your units here, right? Remember, that's the time in weeks. So I'm going to put the number in there, but I have to convert it into that number into weeks, right? So if it's 299 days, there's 7 days in a week, it's 299 over 7. Now I wouldn't bother decimalizing that. I'd leave that as a fraction. So if I want to convert 299 days into weeks, it's 299 over 7. I'll leave it like that and pop that into the formula. There's no need to decimalize and approximate that. Let your calculator worry about that, right? So I'll sub the value in. So then y is equal to 18.6 times sine pi over 26 by 299 over 7. And then I can just dump that whole thing into my calculator, and it comes out at about minus 18.6. So it's minus 18.6. It says to 1 decimal place. So it's minus 18.6 degrees Celsius is the temperature on Christmas Day. Okay, 299 days after the start of March. So that's cold. That's definitely a white Christmas. All right. And then part 3, it says for how many days over the course of the year is the temperature at the South Pole greater than 11 degrees Celsius? So for how long, how many days over the course of the year is the temperature greater than 11 degrees Celsius, and you're asked to give your answer to correct the nearest day, all right? So if you look at your graph here just in very simple terms, just to kind of make sense of this in my own head, okay? If that's 52 weeks there, then that's 26 weeks. Remember, that's the halfway point there. And 11 degrees is in between these two. Say 11 degrees is around there somewhere, right? So if I go across from there, there's 2 times in the first half of the year when the temperature is equal to 11 degrees Celsius. And in between those 2 times, the temperature is above 11 degrees Celsius. So I'm trying to find these 2 times. What are the 2 times during the year that the temperature is equal to 11 degrees Celsius? And then in between those 2 is when it's above that, right? So again, to find those 2 times, the 11 degrees Celsius is the temperature. I'll put the 11 on the left-hand side, and I'll solve the equation I end up with. So 11 is equal to 18.6 times sine pi over 26t minus 1.8, and I'll go ahead then and I'll solve that. Sorry, there should be a minus 1.8 there, but the answer is correct. Okay, so the minus 1.8 should be in that formula there, but the answer is correct when you sub the value in. All right, so there's a minus 1.8 there. So again, we'll add 1.8 to both sides to remove the minus 1.8 from this side. So I get 12.8 is equal to 18.6 times sine pi over 26t. Again, divide by that number to get rid of it from the right-hand side. So if I divide both sides by 18.6, I get 12.8 over 18.6 is equal to sine pi over 26t. And then remember, to get rid of cosine, I used inverse cosine. To get rid of sine, I'll use inverse sine. So the inverse sine of both sides. Here's the inverse sine of the left-hand side, okay, will equal just pi over 26t. And if I just get the inverse sine of 12.8 over 18.6, it comes out about 0.759. Okay, so 0.759 is the answer there. And then again, just divide by pi over 26. So t then is equal to, it's about 6.3 weeks. Okay, now I can turn that into days now if I want to. I'll just leave it in weeks at the moment. I'll convert my answer to days. There's no problem with that. So that's about 6.3 weeks there. So it takes 6.3 weeks to get to a point where the temperature is 11 degrees Celsius, right? Now, like we did in the previous question, to find the second one, let me just use the symmetrical shape of the graph, right? So you can see this N shape here, which is when the temperature is above the center line here, goes from 0 to 26. So if the first time here is 6.3 in from the left-hand side, the other time will be 6.3 in from the right-hand side, and the right-hand side here is 26, not 52, because it's just this N-shaped part here that we're dealing with. Okay, that's the bit that's symmetrical, right? If I draw a line down here, the right and left-hand side of the entire graph are not symmetrical, but this bit is, right? So it's 26, take away 6.3 would be the second time. So 26 minus 6.3 is equal to 19.7 weeks. Right? So that's 6.3 weeks when the temperature hits 11. It stays above 11 until we get to 19.7 weeks and then drops below that. So the difference between those two will be my answer. So the time it's above 11 degrees Celsius, it's going to be 19.7. That time there, take away 6.3, that's going to give me this bit here. So it's 19.7, take away 6.3. Okay, and that comes out at about 13.4. And then it wants the answer in days, so I'll multiply that by 7. Okay, and to the nearest, that's like 93.8. So to the nearest day, that's 94 days. So over the course of the year, it'll be above 11 degrees Celsius for about 94 days. But again, very, very helpful to have drawn that sketch to begin with. Not only did it make it, did it answer a couple of the questions for me, but it made it much easier to find those values there when I got to the end of the question. So the next question then, question 15.3 on page 209, looks like this, okay? So it says that in a particular area, the populations of a species of predator, Px, and its primary prey, Py, both vary approximately sinusoidally over time. So we met the word sinusoidally in the previous question as well. Sinusoidal means it just makes that repeating wave shape. Okay, so this symmetrical wave shape. So the graph, when it gets going, it just creates that wave shape. So all four of the graphs we're dealing with here, both sine and cosine, negative sine, negative cosine, they're all sinusoidal. They all kind of, the basic repeating shape varies slightly, but when they get going, they all just create that repeating wave shape. So it doesn't mean sine. Okay, sinusoidal just means it forms a repeating wave shape, which all of your trigonometric, which all your sine and cosine functions do. The tan one is not sinusoidal, it doesn't create a repeating wave, remember, it's discontinuous. But both sine and both cosine curves are sinusoidal, all right? So it says the diagram below shows how the prey population changes over an observation period of 18 months, and you can see that we go as far as 18 months on our x-axis there. So it says in part 1 that Py, the prey, which is, remember, is the prey population, can be modeled as a trigonometric function of time, which is t in months. Which of the following best represents the graph shown above? And justify your answer. So if you notice here, the four options here, that again, we've got a positive sine graph here. We've got a negative sine graph. We've got a positive cosine graph or a negative cosine graph. So which of the four basic shapes is it? That's what the question is basically dealing with here. Well, you'll notice that the top of the curve is up here somewhere. The bottom of the curve is down here. And the graph begins somewhere in between those two. So it's not starting at the top or bottom, so it's not a cosine graph. I mean, just remember the cosine graphs start at the top or bottom. So it's one of the sine graphs because it begins in the middle here. And remember, a positive sine graph, like the one we had in the previous question, starts in the middle and goes up. So a positive sine graph, if I was to draw the basic shape, looks like that. Start in the middle, goes up in an N, down in a U, and then repeats that. So when you turn that upside down, we get the negative sine graph. You get the U first and then the N. And that's what we've got here. So as we start in the middle and go down, so that's a negative sine graph. So it's this guy down here. All right, so that's the one that best models this. It's a negative sine function. And if you're asked to explain why, the reason the examiner would ask you to explain why is simply to separate out who actually knew and who just guessed, who did a quick pick there, who just closed their eyes and stabbed the page with a pencil and got lucky. Right, so you don't have to give him an essay here. Any indication that there was some thought process involved here is all he's looking for. So in this case here, if I just indicate that it starts in the middle and goes down. So it starts in the middle or at its central value or something along those lines there, which indicates it's some kind of a sine curve, and it goes down. So it starts in the middle and goes down. That means it's a negative sine curve. So anything along those lines there, just give the examiner some indication that I didn't just pick one out of fresh air. There was some thought process involved here. So it's a negative sine graph. Okay? So the next part of the question then, on the next page, part 2, it says find the values of a, b, and c. So now that I've identified what the function looks like, I now have to identify the values of a, b, and c. Okay? So remember, we've established here that the function looks like this, that p of y is equal to a minus b times sine ct, right? And it says find the values of a, b, and c. A and b are natural numbers, and c is between 0 and 2 pi. So again, he wants this here measured in radians. It's between 0 and 2 pi, so we're taking the radian measure here. So if you remember then the three numbers, first of all, the number by itself here is your center line. I want to work that out first, okay? So if you look at back at the graph again here, if I do want to find out what my center line is, so if I go across from the very top of the curve here, like that, you can see that's what, if you read it off the graph, that's 460. That's the top of the graph. And if I go across from the bottom here, like that, you can see that's 180. So reading from my graph, the top and bottom of the graph are 460 and 180. So what that means, remember, is that my center line will be halfway between those two. So if I just get the average of those two, so 460 plus 180 over 2, okay, that's 640 over 2, which is 320. So 320 is the center line. If you look at your graph, that does seem to be where the graph begins. It does seem to start at 320 on the vertical axis. So that's my value for A. So A is equal to 320. Just make sure you specify that. He said find the values of A, B, and C. So A is 320. So I'm putting my formula together now, as I will in a second. A is 320. That's my center line. Now remember, this number here, B, that's your amplitude. That's how far above and below the center on your graph, or the center on the graph will go, right? So you'll notice here that we're going up as high as 460. So to get from 320 up to 460, I'm going up by 140. And to get from 320 down to 180, I'm going down by 140. So I'm going up and down by 140 there, so B is 140. It's your amplitude. So I could say that, look, that's 460 minus 320. That's the top point of your graph. Take away the center line is 140. Or the center line, 320, take away the bottom of your graph. That either of those two will give you your value for B, that B is equal to 140. Okay? So B is 140. So we've got minus 140 sine like that. And then finally, what I need to know now is I need to find my value for C. And remember, this number here is related to the period. Remember that the relation we talked about in the previous lesson, a full circle divided by that number there will give you the period, or a full circle divided by the period will give you that number there, right? So if I go back to my graph, you can see that the graph here, so there's my center line there, okay, running across at 320, kind of comes across like that. So my graph goes down in a U, up in an N, and back. And at this point here, that's when the graph starts repeating itself. There's your basic negative sine shape. So if I come down like that, you can see there's the period. The period is 12 months. So we're on a yearly cycle here, which makes sense. It's 12 months, okay? So what that means then is the period is 12 months. So a full circle, 2 pi, divided by the period divided by 12 is pi over 6. And that's my value for C. And that is between 0 and 2 pi. So you can see that's pi over 6 t in there. Okay, so there's my values for A, B, and C. And there's the end. That's what the formula now looks like from now until the end of the question. So I've now established what the question looks like. Okay. So in part 3 of the same question, for how many months each year is the prey population less than 250? Okay, so again, that's another one of those. Remember, your formula looks like this. So that Py is equal to, it's 320 minus 140 times sine pi over 6t. And again, that number given the question, 250, that's a population value. That's going on the left-hand side. Okay, so that same equation we've met in the last couple of questions. So 250 is equal to 320 minus 140 times sine pi over 6t. So if I subtract 320 from both sides, I get 250 minus 320 over here. That's minus 70 is equal to minus 140 times sine pi over 6t. And then divide by this number here. So minus 70 divided by minus 4. You can leave it like that, obviously. Minus 70 divided by minus 140. But you might recognize that's just a half. Now I can leave it as minus 70 over minus 140 because it's going to my calculator anyway. But that's just a half there, okay? That's what's equal to sine pi over 6t. Then if I take the inverse sine of both sides, so the inverse sine of a half is equal to just pi over 6t. And if you put that into your calculator, the inverse sine of a half is pi over 6. So when you divide both sides by pi over 6, you get that t is equal to 1. So t is equal to 1, and remember the time is in months. So what's the second time? Well, remember, if you remember, again, taking the basic shape of our graph like that. So there we go. We've got our the graph does this. It's a negative sine graph does this, and does that. And we worked out in the previous graph that the period in the previous part of the question that the period here is 12, right? So that's 6 there like that. And our center line here is 320. And then that brings up here as far as 460 and down here as low as 180. So 250 is down here somewhere. It's below 320, right? So that's 250 down there. So you can see there are the two times during a year, okay, when the population is less than 250. And we know that's 1 week, or sorry, that's 1 month there. That's our first answer. So again, we'll use the symmetrical shape of the graph. If the first time is 1 month in from the left-hand side, the second will be 1 month into the right-hand side. Remember, the right-hand side is 6. It's half the period because this U is half the period and that ends the other half. So if I come in 1 from this side here, that's 5. So the population drops below 250 after 1 month and comes back above after 5 months. So the gap between those two, 5 minus 1, it's going to be 4 months that the population is below 250 in the course of any given year, right? Now, part 4 then, it says the predator, on the next page, says the predator population Px can be modeled by this function here. So Px is equal to 240 plus 80 times cosine pi over 6t. Okay, and again, again in radians, same time. It says plot a graph of P over the same 18 months, Px over the same 18 months. Now, again, what I can do if I want to is I could now fire up my calculator like we did back in the first question in this lesson. I could type that formula in. I'd follow the lead of the previous graph. So your graph back on page 209, you can see it goes from 0 to 18 in threes. So what I could do is I could just type in this formula here, and my table range go from 0 to 18 in threes, get those numbers, plot them as points, join them together. That's perfectly fine. Okay, if I want to do that. So if you want to do the graph that way, if you do the graph that way, what you get, if I go in the same thing there, 0, 3, 6, 9, 12, 15, and 18, then if I do that, the numbers I get are 320, 240, 160, 240, 320, 240, and 160 again. So that's what. So if I just use the table function the very same way I did in the first part of the question, I get a set of numbers that look like that. So if I go back to my graph now and just plot those numbers, okay. So what I've got there is at 0, I've got 320. Sorry. So we've got 320 there. All right. Then at 3, I've got 240. So 3 at 240, that's about there. All right. Then 6, it's 160. Just down there. 9, we're back up to 240 again. Then 12, we're back up to 320. 15, we're back at 240. And then finally at 18, we're back at 160. Down here. And I can just join those together then, just to form a very rough curve. Something like that. Okay? So that's what the graph looks like. Right? And then finally, you can see then in part 5, it says, use your graph to estimate the length of time over the course of the entire observation that the predator population exceeds the prey population. So when is the predator, remember that's the predator population there, Px. That's that graph. So remember, the predator population exceeds the prey population when the Px graph is above the Py graph. So that essentially means this bit here. Okay? That this bit here, sorry, that bit there and that bit there, they're the two places where the predator population exceeds the prey population. So if I go down from here, from your graph, you can see that looks like that's about 4, I think. Maybe a little bit more than 4. For my graph, let's call that 4. Yours might be a little bit more accurate than mine. Okay, and you can see that the two of them are equal here again at 12, and then that looks like 16, right? So it looks to me like that's a spread of 4 months there, and that's another spread of 4 because it doesn't say over a single year, it says over the entire observation. So it's 4 and 4. It looks like the answer there is 8 months, reading that from the graph. So our final question then for this lesson is question 15.4. It's on page 212, and it looks like this. So you can see it says the volume of air, V, in centimeters cubed, inside the lungs of a subject during normal breathing was recorded over a period of 15 seconds. So again, you can see that on our graph, 15 seconds down here, all right? So what it says there is, in part 1, it says the tidal volume is the volume of air moving in and out of the lungs during normal breathing. Use the graph to find the tidal volume. So notice here that according to the graph, that's the lowest volume of air in the lungs during normal breathing. That's obviously when you've just breathed out. And you can see that's about 22 on the graph, but be careful, you can see it's in hundreds of centimeters cubed, right? So it's not 22 centimeters cubed, it's 2200 centimeters cubed, all right? So that's 22 there, but if you multiply it by 100, that's 2200 centimeters cubed, okay, is the smallest volume of air in the lungs during normal breathing. That's when you breathe out. And if I go across on the top there, that's 27.5. You can see that's halfway between 25 and 30. And if I multiply that by 100, that's 2750. Right? So the difference between those two is the amount of air that's moving in and out of the lungs during normal breathing, and that's 550. Okay, so it's 550 centimeters cubed. Is the tidal volume, the volume of air moving in and out of the lungs during normal breathing. And it says, what's the subject's breathing rate in breaths per minute? Well, notice there's one full breath there, right? Because you can see that you breathe in and you breathe back out again. The volume of air in the lungs goes up to its highest, then back down again. That's a single breath. That's one shape of the graph. Remember, it just repeats from there. You might notice it's a minus cosine graph. We'll get to that now in a second. But that's the idea there, that it takes 4 seconds. So one breath takes 4 seconds. So if one breath takes 4 seconds, if I just divide 60 seconds, remember a minute is 60 seconds, so 60 divided by 4 is 15 breaths per minute. Okay, so it's 15 breaths per minute is what we're dealing with, because each breath takes 4 seconds according to the graph. And part 3 on the next page says the functional residual capacity is the volume of air remaining in the lungs after breathing out during normal breathing. Use the graph to find the functional residual capacity. So you can see that's the number we had here a moment ago. That's the 2200 we had there. That's your functional residual capacity. It's the amount of air left in your lungs after you've breathed out. It's 2200 centimeters cubed. So those 3 calculations are all very simple. They're just based on looking at the graph which is provided for you, right? But part 4 then, you can see it says it wants us to choose which of the following formulas best represents the graph shown above. And again, you can see it's a positive sine graph, it's a positive cosine graph, a negative sine graph and a negative cosine graph. And if you look at the basic shape in this case, okay, so the basic shape of our graph here, you can see it starts at its lowest point, goes up in an end, back down again, and then repeats that basic shape. That basic shape, remember, is our minus cosine graph, the one that starts at the bottom. All right, so in part 4 there, I'll comment on that. That's the minus cosine graph, and the reason for that, again, I said he's only asking for a reason to separate out who just picked one out of fresh air. So it's the minus cosine graph. It's that one there. That v of t is equal to p minus q times cosine or t. Right, it's the minus cosine graph, and we're not actually asked to explain why. All right, but if you're in any doubt in the exam, I'd tell the examiner why. Okay, because it starts at its lowest point. So a minus cosine graph starts at its lowest point. And then find the values of p, q, and r. So it's like we did in the previous question. We identified from the graph a moment ago, the top point is 27.5, and the bottom point is 22. So if I add those two together and divide by 2, I'll get the average, which is a point that's halfway between them. That's 49.5 divided by 2, which is 24.75. And remember, that's my center line, that's my value for p. Okay, so p is 24.75, right? And then to find the q, remember q is your amplitude. It's how far above and below the center on your graph will go. That's the difference between this number here and this one, or this number here and this one, okay? So let's say 27.5, your highest point, take away your center line, 24.75. That will give me an answer of 2.75. And that's my value for q, that's my amplitude. We're going up and down by 2.75, okay, to get to the top and bottom of the graph. That's my value for q. And we're to find r, then you divide a full circle by the period. So remember, the ratio between that number there and the period is a full circle divided by one of those numbers gives you the other one. And again, we're working in radians here because it said that r is between 0 and 2 pi. So a full circle is 2 pi. And we worked out back in part 2 that the period is 4 seconds. One breath takes 4 seconds. So we'll divide that by 4, which is the answer pi over 2. That's my value for r. And what that means, the entire form, if I wrote it down, is that v of t is equal to 24.75. There's my center line p, minus 2.75. There's my amplitude q, times cosine pi over 2 t. Okay, and that's the formula we've got there, right? And then the last part of the question, just to finish up. So it looks like this, part 5. It says the diagram below shows the effect of exercise on the subject's normal breathing. So there's the normal breathing there at rest along here. And then suddenly you start exercising. It says, based on the diagram above, what effect do you think exercise has on the formula found in part 4? All right. So the formula you had in part 4 is one we just wrote down there, that v of t is equal to 24.75 minus 2.75 times cosine pi over 2t. Well, just notice something here if you look at your graph, right? So there's the center line of the graph when you're at rest, right? That's the 24.75. If you look at when you're exercising, you can see the center line is up here somewhere now. So quite obviously that number there has increased. That's all the exam is looking for me to mention there, okay? That the 24.75 will have increased because the center line has gone up. So when you're exercising, the center line of the graph goes up, so that will have increased. Notice as well here that this is the amplitude. So there's the amplitude there, and the amplitude there, we're going up and down. That's the 2.75 in this graph here. You can see the amplitude over here is much bigger. So that number will have increased as well. So the 24.75 and the 2.75, they both have gone up because the center line and the amplitude have both increased from the graph. Now, if you notice here, there's one breath, if you like. There's one basic breath there. There's another single breath there. So you can see that's if you like the breathing there. Just pick any 2 points in the graph if you like. So maybe to make that a bit easier, if you want to see a single breath there, say there's a peak there, there's a peak there, right? So that's one full breath here. What about over here? Say there's a peak there, and there's a peak there, right? So it looks like that. So does it look that different? Well, for me, that doesn't look terribly different. Maybe it's a little bit bigger, but the key thing here is any answer I give should just indicate that I understand that that number there is related to the period, okay, and how often it takes to repeat this. So even though you might feel in your own heart and soul, and having done biology, that probably the breathing rate, the period should change, I'm not sure there's very much evidence for it on the graph. That it looks to me like the period is the same, so that number is probably not going to change very much. But if you said, for example, that it looks like the breathing has sped up a bit, so that number will change. Okay, that number there will change, or the breathing has slowed down. Any comment like that shows the examiner, I understand, that that number there is related to the breathing rate, the period, and that's all he'd be looking for there. So certainly the first two numbers, the 24.75 and the 2.75, will both have changed. They both have increased. It looks from the graph that the pi over 2 may not have changed very much because the period doesn't seem to have changed all that much. And these kind of additions to the graph here show the examiner what my thought process was. So there's 4 really good questions dealing with trigonometric functions, a really important part of the course. So we're going to have a look at it in the next lesson. We're going to start having a look at trigonometric equations.